Okay, again, one of the big ideas in pre-calculus and calculus, it's a central idea in calculus, is the idea of a rate of change. And in pre-calculus, we get used to the whole idea of rate of change. So I want to talk about the idea and also a little bit about how you use function notation and graphs and how rate of change relates to all that. Okay, it's a pretty good chunk of stuff, but if you kind of bookmark this class, assuming that I stay coherent through the whole thing, might serve as a good reference all the way through a calculus course, if you have one of those in your future. Okay. Okay, so simple question. Last time, and I did spend a fair amount of class time, first 30 minutes or so, taking data on the lunar orbiter, which was making a critical pass by the moon. Okay. Now, what I get from the data, and I'm intentionally not looking at what they say the path is, I'm conjecturing that the moon's going this way at about 2,000 miles an hour. Okay. Spacecraft is kind of going along with it. It's orbiting the moon. Okay. Now, it was also, Earth was influencing that orbit in ways that we don't need to talk about because you have to understand vectors and stuff. I can show it to you intuitively, but don't worry about it. Okay. The closer it gets to the moon, the stronger the moon's gravity. So the closer it gets to the moon, if it's going to stay in orbit, the faster it has to go. So it kind of comes around like this. Okay, it's in an orbit that brings it much closer to the moon. Okay, it's been in that orbit, or it had been in that orbit for the better part of a week. Went way out here. Now it's coming in and it passes the moon really fast. Okay. Except I think the way they did it was they came around and passed the moon and made a quick pass here, which spit them out in this direction away from the moon. Since the moon is moving this way, when you get spit out in this direction, it slows you down with respect to the Earth. Okay. So it slowed down from about 4,000 miles an hour, about 500 miles an hour, you know, speed of a jet plane. Okay. And that's where it's been for a while. And that's got it away from the moon. So it's not being pulled along with the moon anymore. So now I think it's falling back to Earth. Okay. Now the Earth is here and it's falling kind of in this direction, but the Earth's going to pull it in. So it makes a quick pass around the Earth. Okay. But it hits the atmosphere and, you know, it would burn up if it didn't have a heat shield, but you got the heat shield, and that prevents it from burning up. Hopefully, especially if there are people in it. I mean, they got some good traffic test dummies in there. You know, you think that they don't want to burn those up either, but if they're going to burn something up, better to burn up the dummies. Okay. Yeah, they want to test it because they've never hit the Earth at that speed before. They've never re-entered at the kind of speeds they're going to re-enter at, like 23,000 miles an hour. Okay. Now, all that is really simple first year physics. Most of it. Really fine-tuning the orbit so it works. That takes a little more than just first year physics. That takes advanced classical mechanics. Okay. A lot of which I don't know. A lot of which I couldn't do. I could probably get myself back up to speed on it. But it's been 50 years. Okay. And I wasn't that great at it comparatively to other physics majors. As good as electromagnetism. Okay. I don't know why I was bad at classical mechanics, but I'm just stupid that way, I guess. Still. Okay, well, enough biography, but we're talking about a rate of change now. So one thing we calculated Monday, I think, was for 2,000 miles from the moon. Or at 1,000 miles, moving at 50 miles per minute. Okay. So I'm just going to review that calculation because it's pretty obvious. Okay. If you're 1,000 miles away, moving at 50 miles every minute, just imagine 1,000 miles away. Okay, Texas. Okay. Got daughter and grandson in Texas. They're a little more than 1,000 miles. So as a crow flies, pretty close to 1,000 miles, 1,100, something like that. So if I wanted to go from here to Texas, and I was able to do 50 miles every minute, how long would it take me to get there? 20 minutes. Okay, I just quick calculation. Okay, so okay, there's a question. And almost by the time I got the words out of my mouth, somebody went, good mental arithmetic, good skill. Okay. Although it's a fairly easy calculation, most people won't do that. Okay. And it's a good thing, good skill to build on. Okay. Okay, well. Obvious to some, but let's do the calculation. Well, first of all, how far equals how fast times how long, right? If you're traveling down the interstate at 70 miles an hour, how far do you go in 4 hours? Okay. So, and you can't signal that, and the eight's too hard to, I guess a couple of like that, maybe. Okay. I didn't know you had it in your head. Okay, how far equals how fast times how long? Okay. Example. That doesn't involve division. That doesn't involve division. That should be more obvious. Okay. If you were making $70 an hour and worked for 4 hours, how much would you make? Everybody can do that quick. Okay, because everybody understands that. Okay. So this is pretty obvious. Another example. $70 per hour for 4 hours. Most of them take that, right? Okay. If that's not obvious, you've never been employed. Okay. You've never worked for hourly wage. But almost everybody is almost universally obvious. Okay. Maybe they can't do the multiplication in their head, and that's a little bit sad, but it goes back to the overuse of calculators. Some people have to punch that into a calculator. Okay. And I don't think that's a good state of things. So if you do in your head, great. If you can't, I know you can punch it into a calculator. You know what to do. Okay. And that should be obvious. I did write obvious rather than oblivious, right? Okay. And nobody in here is oblivious. So can make that joke, but anybody happens to be watching this, don't appreciate the joke, stop being so oblivious. Okay, now. No, these aren't formal calculations. I was going to do the formal calculations. But I'm going to call these intuitive calculations. Now, you remember how we explain the laws of exponents, which aren't really involved with this, but you know, by analogy, we explain the laws of exponents like 2 cubed to the 4th power means 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2. And then we abstracted that to the law of exponents. It says a to the b raised to the c is a to the b times c. So we got a rule. Okay. People never remember the rule unless they know what it means. Like 2 squared to the 3rd power. Okay. 2 times 2, 2 times 2, 2 times 2, 6 of them, 2 to the 6th. Okay. That makes sense of the rule. This makes sense of the rule that you're given. And almost everybody's given it. For most people really understand it. So most people think, use formula. Got formula. Oh, forgot formula. Can't figure out how much money I make. Okay. Nobody's that bad off with dollars per hour and dollars. Okay. Some people are. I mean, some people just have, their brain just isn't wired to do it, but they have other aptitudes, so they probably ought to pursue those other aptitudes. Okay. Okay, well, out of this, we get the idea that if you multiply rate times time, you get the amount. This is an example. These are examples of rate multiplied by time. Okay. So for amount equals R times 2 or whatever. Okay. Whatever formula you happen to see, whatever letters people tend to use. Usually it's R and T. That letter can vary. Okay, so divide both sides of this by T and you get rate equals amount over time, right? Or if you want to find the time, amount over rate. To solve this equation for R, you're going to divide both sides by T, right? So I can kind of write that calculation over here. I'm going to write it kind of small because, okay. This gives you this. Dividing both sides by T. Okay. So if I tell you, now I tell you, okay, travel 300 miles in 5 hours. How fast you moving? 60 miles. Don't say it, but 60 miles an hour, right? You can do the, you divide 5 hours into 300 miles. An easy division. 5 into 30 is 6, and you're going more than 6 miles an hour. And then you can check it out. So, okay, let's say 60 miles an hour times 5 hours. 60 times 5 is 300. Yeah. Or count them in your fingers: 60, 100, 180, 240, 500, 300, 500. Okay. Make sense? All right. Okay, so this gives you this, and this gives you this, okay? So now we've got a formal way of dealing with rates and time. Okay. Now, here's some data from early when I was still trying to figure out everything that was going on, okay? This is the time since the thing was launched. 4 days, 22 hours, 34 minutes. Okay. And this is how far it was from the moon. Now here was 5 hours, 9 minutes and 5 days, 9 hours and 14 minutes. It's days, hours and minutes, okay? Okay, so my question is, at what rate was it approaching the moon? It was this many kilometers. Actually, this is miles, isn't it? Yeah, it's gotta be miles, it's not kilometers. I wrote that down in miles. I mean, I wrote down kilometers. I actually did a lot of reasoning with this while it was happening. Down around this time, and I still had kilometers up here. So one of my greatest videos has a terrible flaw in it. I make sure there's always a terrible flaw so people don't take me serious. Okay. So I'm trying to puzzle out what directions this thing moving relative to the moon and all that stuff. And that gets into a lot of complicated vector diagrams and stuff like that. Not really that complicated, but they look complicated until you know what you're doing. Okay. Well, I did these calculations in my head. I think they're pretty correct. So my question is now, between this time and this time, I'm going to ask you to tell me how fast it was approaching the moon. It's this far away at this time, this far away at this time. Okay, see if you can work that out. Okay, now what we have to see is we want some distance between here and here, right? So that how far is, well, it's about 12,000 miles. Okay. And how long did it take? That's the time we want to use. We don't care about what the clock says. You know, the clock could have started back at midnight when the Huns invaded Rome. Okay. But the time it took to get from here to here would still be the same. You know, we'd have to put this in years, 2,000 years, so many days, so many hours, so many minutes, okay? So we'd have to have a lot more information here, but what you want to get down to is how many minutes did it take to go from here to here and how far did it go, okay? So for your data, you have to start with how far it went and how long it took. Another analogy, if you're at mile 300 on I-81 right out in front of the college, okay? At 2:30 in the afternoon, you wouldn't divide 300 by 2:30 in the afternoon. Now, if you started at mile 0 and went to mile 300, then you would divide by not 2:30, but 150. Okay, 150 minutes. That means you'd have been driving at 2 miles per minute Okay. Uh, you probably don't want to go that fast. You get pulled over or you kill somebody. And there'd be a truck, there'd be a couple of trucks going up a hill. And you know, how are you going to get around those at 120 miles an hour? I don't think you want to try it. Actually, you probably wouldn't want to try it because you're young and foolish, but that's another story. Okay. Might be fun to try, but you'd be taking a big risk with the law, with your life, with those truckers who will beat the crap out of you. Okay, so you don't want to do that. Just to clarify what these numbers mean, because we don't need to really do any fancy calculations. Okay, the 4 and the 5 means this is on one day, this is on the next day. This is at 22 hours. Now, hours on a 24-hour clock, it's a 24-hour clock, start at midnight. 22 hours later, you're at 10 p.m., 2 more hours till midnight, okay? So that's like 10:34 in the evening. This is on the next day at 9:14 in the morning. How many minutes are there between 10:34 in the evening and 9:14 in the morning? How many minutes? One way to think that is, well, if we went to 09:34, then it would be an even number of hours, right? But we're 20 minutes short of that, so 20 minutes short of that many hours. How many minutes is that? 60 minutes in an hour. Okay. From this to this on day 4 to this on day 5. Okay. It's like how many minutes is that? There are a couple of ways to do it. You can count. Okay. You go to 23:34, that's 1 hour, right? 24:34, well, that would be 0:34, that'd be 2 hours. Okay. And then on up to 8:34 would be 8 more hours, right? So you'd have 10 hours. Okay. Now we don't go to 9:34, we could, but we'll stop at 8:34 and then figure out how many minutes there are from 8:34 to 9:14. Just draw a picture of the clock. 34 minutes, you go around to 14 minutes. Okay. Couple of ways to do that. You're 20 minutes short of being at 34. So you're 20 minutes short of 11 hours. Okay. So 22. Eight 34 is 10 hours. And then 8:34 to 9:14 is 40 minutes. .600 minutes plus 40 minutes is 640 minutes. Okay. So whether you totally visualize that and understand, think about it, you can visualize it. Okay. So it's 640 minutes. Now the question is, how far did it go? And then what do you do with those results, and why in the world is the stupid camera Zoom so far back, nobody can read anything. It's getting irritating. Okay. Yeah, I got better things to do than keep an eye on a misbehaving camera. I've got misbehaving students out here. Doggone it, I got to keep an eye on them. I can't pay attention to the camera. Okay, well, just another irritation in the life of somebody who's trying to deal with little technology. Okay. Not sure where I failed to start recording, but probably about here or so. Just quickly. Okay, so how long is 640 minutes? It's not 4:22:34. That's just the time on the clock. Doesn't tell you how long it took to get from here to there. You gotta know how long it took to get from here to here. Okay. So that's how long. 640 minutes. How far is this? And that's 12,255 miles. That's the same thing you got in my head, you got in your calculator, so your calculators are working. How fast is, well, it's 12,255 miles or 640 minutes. This many miles divided by this many minutes. Same calculation you would do if I said you travel 300 miles in 5 hours. Take how many miles, how many hours? Now we divide by minutes rather than hours. That's okay. 19 miles per minute is pretty close to 1,200 miles an hour. Okay. And, you know, fighter jets go that fast. Okay. Bullets go faster than that. Okay. So that's what we get. Now, this is an average rate because the Earth's gravity at a distance of, well, at these distances is weaker. Okay, Earth's gravity at distances of around 230,000 miles is weaker than the moon's gravity at a distance that's only a fairly small fraction of that. Okay. This is less than 1/10 of that distance. So at this distance, the moon's gravity is stronger, but maybe only by 2 or 3 times. At this distance, it's many times stronger. Okay, could be 20 or 30 times stronger. Just ballpark calculation off the top of my head with ratios. And knowing the ratio of the moon's mass to the Earth's mass, you got to be a lot closer to the moon than you are to the Earth, because the Earth has a lot more mass than the moon. So to give a distance, it pulls hard. And the pull goes as an inverse square. If you get twice as far away, you only have 1/4 of the pull. Okay. But it's so much closer to the moon than the Earth that for most of this distance, the Earth's gravity is almost irrelevant. Now, what happens is the pull is changing, so the speed changes faster and faster. Okay, as you get closer and closer to the moon, you're picking up more and more miles per minute. If you're at this distance from the moon in a minute, you don't pick up nearly as many miles per minute as you do here. Okay. Anyhow, so we say that this is the average rate at which a satellite is approaching the moon. Now, everybody said, you think that that's the rate is the same all the way from this distance to this distance? We said, no. Okay, intuitively, no, it isn't. But I just explained a little bit about why, just add a little color to the situation and give you some idea of why we want to talk about an average rate. Okay. Okay, so there you got it. Okay. If you ignore the Earth's pull at 6,000 miles, it's going to be picking up speed 9 times as fast as it was at 18,000 miles. That's because 18,000 is 3 times 6,000, and the force is an inverse square force. Means if you're 3 times as close, you're going to be 3 squared or 9 times the 4. Okay, you don't have to keep that in mind, but if you have to watch this when you're talking about rates in the pre-calculus class, it could be pretty illuminating. Okay, it's a pretty clear example if you understand just the idea that the closer you get to a planet, the faster you pick up speed, because the force falls off rapidly with distance and increases rapidly as you get closer. And the mathematics of that is pre-calculus level mathematics, but I'm not going to do all that. Okay, now let's look at what we did. To find the average rate, we found the change in distance and the change in time. Okay. And we abbreviate that as delta x. We're going to let x be the distance. In delta x, delta just means change. And it's just a shorter way of writing change in, so we don't have to write all those words. And it's more compact, so you look at it, and if you understand this means a change in distance and this means a change in time, you can see it at a glance. You don't have to read all those words. Okay, but that's all it means. There's nothing mysterious about it. Okay. If you're going down the interstate, take the change in a milepost, divide by the change in time. And if you find that you went a mile in 44 seconds, okay, that means you were doing a little over 1.5 miles, 1 1/3 miles per second. Okay. It's probably too fast, but that's okay. As long as you don't get caught and hurt anybody, well, I wouldn't make a habit of it. Okay. I think it's really okay, but everybody does it sometimes. Okay. So delta x over delta t. So delta x over delta t, which is your 12,000. I don't want to write too many twos. I think I'll make that work. Okay. And that's what we mean by an average rate of change. Now, more generally, The average rate's a change in y divided by a change in x. Okay. That's what we did over here. We wanted to find the average rate of distance with respect to time. Okay. If in general, if it's a y and an x, whatever y is whatever x is, it's a change in y over change in x. Over here, instead of x, we used x for the distance and t for the time, right? So it's delta x over delta t. We could have done that. But I want to use this form of the definition and apply it to the graph. Okay, so first of all, we're going to apply it to the table. Remember, we made a table for this y equals x squared function. You did quite well with it. We got 4, 1, 1, 4, 0, 1, 4, 1, 4. Okay. So what I want to do is I want to calculate the average rate of change. Between 0 and 1. Okay, average rate of change as we go from 0 to 1. Actually, it matters what direction we go. So we go from 0 to 1. And actually, I don't want to go from 0 to 1. Calculation is too simple. I want to go from equals 0 . It's not T, it's F. Okay. Now, what's the definition tell you? It's the change in y divided by the change in x, right? So all you got to do is, what are your two y values? What are your two x values? Okay, just quickly, I don't remember what was recorded and what was, but your general definition is the average rate of change of y with respect to x is change in y divided by change in x. Okay. Just like what we did here, we did change in distance over change in time. Now this was a delta x over delta t, but it's the change in the first thing with respect to the second thing. Okay, first thing you say when you say rate of change of this with respect to that is change in this and divide by change in that. Okay. Oh, we made this table. I think it's probably on the recording, but just to be sure. Made this table for the x squared function. And that table's easy. We made it. Everybody can make that table. And if you can't, by the time you get to the average rate in the second or really third week of pre-calculus, you will have. Okay. But I think everybody can. So there's your table. We want the average rate of change between here and here. Average rate of change between x equals 0 and x equals 2. I say average rate of change from x equals 0 to x equals 2. I didn't do the word from to conserve board space. Okay. So people got that pretty quickly. Somebody held up. Okay. Well, is that your answer? Yeah. Okay. Then it's okay. How much did x change? How much did y change? Yeah. So what's your average rate of change? Yeah. Okay. So we got quick answers in that. Everybody's good with this. That's really good to see. Okay, now we're trying to write it out more formally so we know what to do when it gets unfamiliar, which is going to do in a minute. Okay. It's delta y over delta x. And that equals, well, I'm going to write this out as 2 minus 0, because if you have two values of x, you're going to subtract one from the other, right? You're going to subtract where you start from where you end. Just like if you go from milepost 10 to milepost 30, you go plus 20 miles, right? 30 minus 10. If you go from 30 to 10, you actually go negative 20 miles in the negative direction. Okay. So we got 2 minus 0 there, and the two, because those are our two x values, our two y values, 0 and 4. So that's kind of a complete calculation. Okay. This is the final 2 over 4 equal to 2. What'd y'all do that for? Actually, you said I did 4 minus 0 over 2 minus 0, which is 4 over 2. Okay, so quickly, let's see, write down the calculation. Oh yeah, and ROC stands for rate of change. It's not a rock, because you don't have a K on the other. Okay, now the rate of change of K is something you don't want people throwing at you. Okay, but the rate of change I abbreviate with respect to WRT because that's the full name of this thing. So what would you do for that? Correction, sorry for the confusion. It's x equals 1/2 to x equals 2. We don't have x equals 4 on this table, although you could calculate. We'll do that in a minute. Just going by values in the table, what do you have? I'll repeat that it's pretty important to lock in what you are understanding by writing out all the words. So you're going to replace some of the numbers in this statement by the numbers that apply here. If you start by writing from x equals 1/2 to x equals 2 and then continue writing this stuff, okay, then you're going to process it a little better. And you're not going to be confused about what to do. You might still be confused about what to do, but you're much more likely to do what it says, okay? Now, I think you're going to get it. Okay, now, and repeat, you really want to imitate this as closely as you can. So you write out average rate, you write out all the words. X from x equals 1/2, and x equals 2. It's delta y over delta x. Okay. Now I'm not going to write 4 minus 0 over 2 minus 0 because I'm not going from x equals 0 to x equals 2, right? I'm going from x equals 1/2 to x equals 2. When x equals 1/2, y is 1/4, right? And when x equals 2, y is 4. So actually, you might have had a little mistake on that. When I said it was okay, but you got the right idea. It's going to be from here to here, 4 minus 1/4. And let's just do some arrows there. Now we're going from here to here. So Put a circle around this. Put a purple circle around this. This corresponds to here to here. This corresponds to here to here. Okay, so we write out 4 minus 1/4 divided by 2 minus 1/2. And that equals, well, 4 minus 1/4 is 3 3/4, if you like. Three 3/4 divided by 1.5, and 3 3/4 is 15/4 divided by 3/2, which is 15/4. Just remind you about fractions times 2/3, which equals 30/12. Comes up more even than I thought it would, which comes down to I mean, it comes out to 2.5. It comes out to 5/2. I did that just by dividing 12 into 30. Then I started doing a prime factorization. I don't know why. It does come down to 5/2. Okay, because you can reduce this. You can divide this by 6. You can divide this by 6. Okay. And I had a little brain freeze up on this, but it's 5/2. A little short of sleep last night. Okay. Or 2.5. Okay, well, let's just see what this means. Now we're going to do another calculation, but we're just about out of time. So I'll just cut to the chase here. If you understand this much, you have a pretty good understanding of rate of change. I'm going to say a little more. Not going to give you time to do anything because I don't want you to go away. I want you to stay forever, but you might have places you need to be. So I can do a graph of, let's say, just this half of the table. I'd have 1 here, 2 here, 1/2 here, I have 4 here, 2 here, 1 here, 1/2, 1/4, 3. And the points that I get on the graph, and people did just real well with this when we did it. So I think everybody understands. Here are my points on the graph, right? And you can connect these with a smooth curve. Looks something like this. Well, what we just did was we went from x equals 0 to x equals 2. Okay, that means a purple calculation went from x equals 0, which corresponds to this point, to x equals 2, which corresponds to this point. Okay. Now, I'm going to draw a straight line from here to here. Then I'm going to make a right triangle. Come over here parallel to the x-axis, come down here right along the y-axis. I'm going to say that, well, if I go from here to here, my rise, actually, I'm going to probably want to label it over here. How far do I rise as I go from here to here? How many units do I rise? 4, right? I go up 4 units. If I go from here to here, I go from y equals 0 to y equals 4. And how far do I run in the x direction? 2 units. Okay. What do I get? If I divide rise by run, I get 4 divided by 2, which is 2, which agrees with what I got up here. You get an arrow there to there. Okay, so there's a depiction of this calculation. And the bigger the rise is compared to the run, the steeper my graph is, right? Okay. That's a slope between the point 0, 0 and 2, 4. Now, complete this, see if I can figure out what color to use. Okay. Now, if I go from 1/2 to 4, that means I'm going from here to here. There's another straight line I can draw. Okay. And there's a rise here and a run here. Well, I don't want to clutter up this picture anymore, but I'll just draw up whatever color this is, pinkish triangle. Like here, my rise, without writing all the words, is I'll write the fraction 3 3/4. The run is 1.5. Okay. That's equal to the average rate of change. Because of course we can circle this, and show they're the same. Well, if you understand every bit of that, you understand the most fundamental idea in calculus. Okay. And the idea that the slope of the graph between 2 points gives you the average rate of change of y with respect to x. Now that's a big chunk to digest. It's a good thing to keep in mind. When you get to the rate of change in pre-calculus, it'd be a good idea to flip back through this video. And I'll be recommending it probably to my pre-calculus classes because I think it worked out pretty well. We got a lot done because y'all were on top of things. Okay. So that's a good way to finish out the course. There's much more we could do with that, but you're going to have to wait till pre-calculus.